All right, today we're going to walk through a physics problem that has been a rite of passage and a bit of a headache for students for years. We're going to break it down step by step and really get to the heart of the beautiful physics principle hiding inside. We're tackling a classic, and it comes from Irodov's Problems in General Physics. Now, if you've been through a serious physics program, you know this book. It is legendary for its challenging problems that really make you think.
And this is our target for today, problem 1.5. On the surface, it looks pretty straightforward, right? A couple of particles, a few vectors, but solving it requires more than just plugging numbers into a formula. You need a really solid physical intuition about what a collision actually is.
So, before we write down a single equation, let's just pause for a second. Let's think purely about the physics. What are we actually trying to describe when we talk about a collision? I want you to really think about this. Forget the math for a moment. What does it mean for two objects to collide in space? What's the one fundamental condition that has to be met no matter what? It's actually this simple. They have to be in the same place at the same time. That's it. This one single idea is the key that unlocks the entire problem. Their position vectors have to be identical at the exact same moment.
Okay, now that we've got our core concept down in plain English, let's go ahead and translate that into the language of physics. And of course, that means bringing back those vectors from the problem.
So next up, we need a way to describe the position of each of these particles, not just at the beginning, but at any given moment in time.
For any object that's moving with a constant velocity, the rule is pretty straightforward. You want to know where it's going to be? Well, you just take its starting point and you add how far it's traveled. And how far has it traveled? Simple. That's just its velocity multiplied by the time it's been moving.
So for particle 1, we can write this out as a nice, clean vector equation. We'll say its position vector at any time t, which we'll call r1 of t, is just its initial position vector r1 plus its velocity vector v1 times time t.
And you guessed it, we do the exact same thing for particle 2. It's following the same rule. So now we've got two powerful equations, one for each particle, that tells us their exact position in space at any moment we want.
All right, now for the really cool part. We can take our definition of a collision and combine it with these two position equations to find the exact relationship that the problem is asking for. We just have to follow the logic. We know that for a collision to happen, their positions have to be equal at some time t. So step 1, we set our two position equations equal to each other. After that, it's just a little bit of rearranging. We're going to get the initial positions grouped together on one side and the velocities on the other. And when we do that, we get our final mathematical condition.
Now, this final equation isn't just a random assortment of symbols. It's telling us something really profound about the physics of what's happening. So let's take a second to really unpack what it means.
This equation beautifully lays out two key ideas. On the left-hand side, we've got the vector r1 minus r2. What is that? Well, that's the vector that describes the initial separation of the particles. On the right-hand side, we have v2 minus v1. That represents the velocity of particle 2 as seen from the perspective of particle 1. We call this its relative velocity. And here it is, the crucial insight. Our final equation shows that the initial separation vector is equal to the relative velocity vector multiplied by just a simple number, time. Now, in the language of vectors, when one vector is just a scalar multiple of another one, that means they have to lie on the exact same line. They must be parallel.
And so here's the final piece of the puzzle. For a collision to actually happen, particle 2 must, from particle 1's point of view, be moving directly towards it. That relative velocity vector has to point perfectly along the line connecting the two particles, aimed just right to close that initial gap. And that is the true physical condition for a collision.